All right. Couple people still need to check into on campus, so if you haven't done that, please do so. Uh, Today we're going to start to go over sequences and series and kind of the fundamentals before we get to probability. Right. What's cool about all of this too is it's also like the foundations of calculus. So we're going to start adding a whole lot of things together um, in ways that you couldn't before. Okay, and that's pretty much what calculus is. It's adding things together uh, over an infinite sequence. Okay, um, sequences in series can be pretty challenging. So please, when I give you homework, one, get it done on time, and two, ask questions about it. It's going to be really, really important, especially over these last like 3 weeks for you guys, uh, to really try and understand this stuff, uh, both for this class and for the next class, because this can lead into calculus really, really well, so long as you actually try and understand it. All right, so sequences and series. We're going to start talking about sequences, and a sequence is any collection that can be ordered. All right, so that means that there's a first term, a second term, a third term, a fourth term, and so on. All right, so it's anything that can be ordered basically, where there's a first, second, third, and so on. All right, in math terms, it's just a function whose domain is the set of positive integers. All right, so there's an f of 1, there's an f of 2, f of 3, f of n. All right, we're going to start to talk about those things as a1, a2, a3, all the way up to an. And all those things mean a1 is the first term, a2 is the second term, a3 is the third term, an is the nth term. So it's just some term later on down the road. All right, and this is called subscript notation. And it's something that you're going to have to be comfortable with, especially for this chapter. All right, so it's kind of the same thing as f of 1, f of 2, f of 3, so that function notation, except we're shorthanding it. All right. So the definition of a sequence: an infinite sequence is a function whose domain is the set of all positive integers. And what that means is that we're just dealing with the first, second, third, fourth, fifth, and so on. And again, they're rewritten right here. And those a's, all of those a's combined, those are the terms of the sequence. Now, if the domain is only the first n positive integers, so only up to n and no further, then the sequence is called finite. All right, so there are two types of sequences. There's infinite and there's finite. Infinite means it just keeps going, and finite means it stops at some point. All right, so I'll pause for a second and let people kind of catch up. And if you have any questions over anything so far, let me know. All right, so the first thing we're going to need to be able to do is to just find different terms of a sequence. All right, so we've got three examples here. All right, and we want to find the first four terms. So we want to find a1, a2, a3, and a4. And we are given the rule, right, an, the nth term, for each of these sequences. All right, so if we start on the left, an is 3 times n minus 2. Okay, so if we just replace that with 1, it's 3 times 1 minus 2. the second term is just 3 times 2 minus 2. All the way up until 4. Or at least that's what we have to find. So right now all this is a substitution. Okay, and then we simplify all this. So 3 times 1 is 3. 3 minus 2 is 1. 3 times 2 is 6. 6 minus 2 is 4. 9 minus 2 is 7. And then 10. And this sequence, and we'll get to this a little bit later, and you don't have to know this right this second. This is called arithmetic, because all we're doing is adding 3 over and over again. Right, so on the first one we added 3 once, on the second one we added 3 twice, on the third one we added 3 times, and so on. Okay, and we'll get to actual rules for arithmetic and geometric sequences later, but right now we just need to be able to find terms. Okay, they're not always that simple though. So sometimes they're just a little bit more complicated with different functions and operations. So in red, for example, we have 3 plus -1 to the power of the term. All right, so again, A1, this is just substitution. And again, we just simplify it. So -1 to the first power, that's still -1. 3 plus a -1, that's 2. -1 squared is +1. 3 plus 1 is 4. -1 to the third power, that's -1. So it goes back down to 2. And then it comes back up to 4. All right, so it doesn't always have to just go up or just go down. These terms can repeat themselves. It can go in a positive direction for a while and then a negative direction. There's a whole lot of different ways that sequences can occur, right? So in this case, we're just going back and forth between 2 and 4. So I want to pause there real quick. Are there any questions about either of those first 2 examples? All right. Sequences can also switch signs over and over again. All right, so it's kind of like what we did on this red example, but we're not adding or subtracting anything. We're constantly going up and constantly going down. So in this blue equation, again, A1, that's just -1 to the first power over 2 times 1 plus 1, right? So that n term can show up in a whole lot of different places. And again, if we simplify -1 to the first power, that's negative. and then we have 1 over 3. Negative 1 to the second power, that's positive, and then we have 5, so 1 over 5. Negative 1 to the third, that's negative, over 7, and then positive over 9. Okay, so again, these sequences can have different patterns, right? So in white, it's just constantly going up. In red, it's switching back and forth between the same two terms. And in blue, it's going from negative to negative, and it's also kind of working its way to 0. Okay. So far, this is only substitution. This is just function notation with different notation, really. All right. So again, are there any questions over this so far? So what's probably a little bit more difficult is working. So up above, we had the sequence and we're working toward a rule. Or sorry, we had the rule and we're working toward a sequence. In this case, we have a sequence and we're working toward the rule. All right, so in these examples, we need to find the rule for the nth term. Okay, and we have to do so by seeing what happens at each term. Okay, so I'm guessing we can kind of figure out the next term, that fifth term, would just be 9. The sixth term would be 11, and so on, right? So you should be able to see the pattern pretty quickly here. You're just adding 2 every time. And this is where it gets tricky, and this is actually a little bit easier in person, but I'm going to try my best in order for you guys to see what's actually happening. All right. We want a function going from the number of the term to the term itself. Right, so we have to go from the first term to 1, the second term to 3, the third term to 5, the fourth term to 7, and so on. Okay, so you have to look at it as a whole, going from the number of the term to the term itself. And you have to kind of recognize a pattern, which sometimes can be super tricky. Okay, but in this case, I'm noticing that if you double the term, we're pretty close. If you double the number of the term in blue, we're pretty close to the actual term itself, right? 2 times 1, that's 2. 2 times 2, that's 4. 3 times 2, that's 6. 4 times 2, that's 8. 5 times 2, that's 9. And it remains pretty consistent that if you just double the number of the term, you almost get the term itself. Okay, but you actually have to subtract 1 in every case. All right, so the rule of this term, of the nth term, would be 2 times the number of the term, and then minus 1. All right, and there are a lot of different ways to get to that conclusion, but you got to look at the blue numbers and see how you get from the blue to the numbers in white, which again can be very tricky sometimes. All right, so you can always test this. Um, Usually when people see this, they think add 2. All right, so they think, and I'll do this in a different color so you don't get this confused. They think that the answer would be n plus 2. All right, that's a good first guess. Okay, but if you test this, a1 would be 1 plus 2, which already doesn't work because a1 has to be 1, right? A2 would be 2 plus 2, which would be 4, and that already doesn't work. So then you gotta modify what's actually happening. You know you're adding 2 over and over again, and in order to add things over and over again, you're actually multiplying, which is how we get 2 times n. Okay, I realize I'm talking a lot. Again, I'm going to pause. Are there any questions over that example? All right, so let's move on to this red example then. All right, so again, we want a rule for the nth term. So just find n basically. You're finding a rule for the nth term, right? Which is an. Okay, so for this in red, we're still kind of doing the same thing. We have the numbers of each terms, and we need to find out how to go from blue to red in this case. But there are a couple things also we have to worry about, right? We should notice overall that we go from positive to negative to positive to negative. So we're switching sign every term. All right, so I like to take this in 2 steps. One for that negative piece, so the switching of signs, and then one for the actual magnitude. So the actual like number, so 2, 5, 10, and 17. All right, so let's work on that negative part first. Whenever you have a sequence whose signs switch every term, we're always going to have -1 to some power. Because -1 to some power will switch between negative and positive as you go up, right? So -1 to the first power, that's negative. -1 to the second power, that's positive. To the third power, that's negative. To the fourth, that's positive, and so on, right? So it switches signs. All right, and then we can just test that piece right off the bat, right? So if we replace n with 1, we get -1 to the first power, but that's negative. If we replace n with 2, that's positive. And then back to negative. Okay, which is actually not quite what we want. So we want positive, negative, positive instead of negative, positive, negative. So in order to fix that, we can just add 1 to our exponent. So then when we do that, we get a positive number in the first term, a negative number for the second term, and a positive number for the fourth term, which matches our sequence. Okay, so we know that that part of the rule is correct. Now we need to actually work on the magnitude. All right, so we have to look and see how we get from the blue term to the red term without any signs, right? So how do we get from 1 to 2, 2 to 5, 3 to 10, and 4 to 17? So, and again, this takes practice, but you should notice that if you square these numbers up here, you're going to get pretty close to your term in the sequence, right? So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 17. Okay, so it's almost there, but not quite. Again, we're just 1 off on every term. All right, so we're going to have some n squared term. And then really all we have to do is add 1 to it. And we get our magnitude. So then we can test it. So we know white is correct. We know that white part is correct. Now we need to check the magnitude. All right, so 1 squared plus 1, that's equal to positive 2. 2 squared plus 1, and then the negative out front, so that's equal to negative 5. Positive 10, and then negative 17. So again, this is very tricky, and you get much better at it with just practice and experience. So I'm not expecting you to be able to do this just yet, but this is a fair question on a test. Okay, so again, I'm going to pause there. Are there any questions about anything that's on your screen? So you're getting the numbers from the blue ones at the beginning. Uh, yeah, those are the numbers of your terms, right? So the first term, that's just A1. Second term, that's A2. Third term, that's A3, and so on, right? We're taking it from the number of the term. So we need to ask ourselves how we get from the number of the term to the term itself. All right, we're asking ourselves how do we get from blue to white or red? So there are different kinds of sequences as well, right? So the ones that we've been talking about are called explicit, and all that means is that um, each term can be found independently of the terms around it, right? So I can find the fifth term without finding the fourth, the third, the second, and the first. Okay, so we have a rule for n, for an, and we can just plug a number into n and find that term without finding any other term. Some sequences, though, you have to find terms previous in order to find the next term, right? And those are called recursive. So each term is defined by terms previous to the next one, right? An example of that is called the Fibonacci sequence, which can be found pretty much everywhere. Spirals of galaxies, hurricanes, right? It can be found in facial features, in like rose petals, flower petals, different patterns in nature. It can be found in a lot of different places. Okay, but the Fibonacci sequence says that uh, our initial term, that's one, our first term, that's one, and every term after that is the sum of the two terms previous. Okay, so what this says, and we'll kind of work through this just so you can see what a recursive sequence is. We want to find the second term, the third term, the fourth term, and the fifth term, given this rule. And now might also be a great time. We're not always going to use n, right? In this term, in this case, it's k. It just depends on the rule. It depends on the person writing it. Usually the Fibonacci sequence is in terms of k, though. Right, so if we work through this, the second term, so if we just replace k with 2, is the two terms previous, so 2 minus 2, plus the term just previous, so 2 minus 1. So then we just do substitution, right? Or a little bit of subtraction first. So this means that a2 is a0 plus a1, which is equal to 1 plus 1, which is equal to 2. All right, you do the same thing for a3. And again, the third term is the sum of the first term and the second term. That's what this is saying. And we can do the same for the fourth and the fifth term. And the fourth term is the sum of the third and the second term. Are there questions about recursively defined sequences? So just to sum this up, two different types of sequences. There are explicit sequences, which we did up here, and even up here, right? So there is a specific rule for the nth term. And then there are recursive, which depend on previous terms. Okay. There are sequences that can be both. So you can define it recursively, or you can define it specifically or explicitly. Usually, though, if we can, we're always going to write a term as explicitly as we can. Is the diagram what you were solving? So this picture is a picture of the Fibonacci sequence, right? So I think it allows me to draw on this. It gives you the first two terms, right? Those are areas of boxes. And all that this diagram is really doing is drawing a spiral from each of the corners. Right, so first two terms, the third term, the fourth term, the fifth term, and the eighth term. So if you draw a spiral kind of around those to each of the corners, you get what's the Fibonacci sequence is actually like diagramming, I guess, or picturing. And this is also kind of goes along with the golden ratio. It's this picture is not important. It's just a representation of what the Fibonacci sequence is saying. All right, so let's do an example of that. And again, this is a recursively defined sequence. This is just an example of it. If you have your books on your laptops, which you all should, this is number 65 on page 648. Not important. We're not going to worry about the textbook just yet. But this question gives you the first term. Right, it gives you A1, and it gives you the rule for each term, and we want to find the first five. Okay, so again, we have A1, and we want to find A2 through A5. And if we just replace 2 into our rule, and actually, right, we can rewrite A2 as A1 plus 1, which we have to do to match our rule. So K is really 1. And AK in this case is A1. So let me rewrite that so it makes a little bit more sense. For A3, we can rewrite that as A2 plus 1, which is 2 times A2 minus 1. So again, each of these terms are defined by the term before it. So A2 is defined by A1, A3 is defined by A2, A4 is defined by A3, and so on. And I realized I did that decently fast. Are there questions about any of that? All right. And the last thing I want to go over are factorials. All right. So again, this everything we're doing today seems a little bit scattered, and it kind of is, but everything we're doing is leading up to actual probability. All right. So if you're thinking to yourself, I don't know how this ties in, these are all like the tools that we need in order to actually do probability. All right. So factorial. Um, if n is a positive integer, n factorial is defined by n exclamation point. All right. So this is the notation we'll be using. And what this means is that we're multiplying every number up until n together. All right, so n factorial is 1 times 2 times 3 times 4, all the way up until the term before n, and then times n itself. Okay, and I'm going to break down the first like 6 terms. Okay, so we need to know that 0 factorial, that's just equal to 1. There is a proof for it. I'm not going to go over it, but we need to know that 0 factorial is just 1. Kind of like any number to the 0 power. It's the same idea. Okay, 1 factorial is just 1, right? Every number up until 1 to multiply together, that's just 1. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. And then 5 factorial is 1 times 2 times 3 times 4 times 5. Okay, so that's how it works. Again, you're just multiplying every term up until the term you're given together. All right. But I'm not just going to ask you to evaluate these, right? I'm not just going to give you 6 factorial, tell you to plug it into your calculator and give me a number. Instead, you have to simplify something that looks like this. Actually, I'm going to make this a little bit smaller so it's a little bit easier to deal with. Just for the sake of screen space. All right. So what we can do is we can simplify this by writing it in the terms that we know. Right? So 8 factorial, it's 1 times 2 times 3 all the way up until 8. And then 3 factorial is 1 times 2 times 3. Okay, so that's just definition of 8 factorial and 3 factorial. 7 factorial, again, is 1 times 2 all the way up to 7. And then we can cancel out common factors. So we start with this left-hand side, and we just cross out everything that repeats. And then we're left with whatever's left. Now you should note that it's not 0 in the denominator. It's still just 1. And then 8 times 1 times 2 times 3 is 48. All right, so 48 then is just our answer. Okay, again, I'll pause there. Are there any questions about what I just did? All right, and then one more example. Is this in green? Okay. So now I'm throwing variables in here. Okay, so we in the numerator we have n plus 1 factorial, and in the denominator we have n minus 1 factorial. Okay, the same rules though still apply. Okay, so n plus 1 factorial is every number up until n plus 1 multiplied together. Okay, so if we think about that kind of on a number line, we have n plus 1. The number before that is just n. The number previous that is n minus 1. And then before that is n minus 2, and so on. All the way down to 0. Okay, so that's how I would look at this. And then on the bottom is n minus 1 factorial. So it's 1 times 2 times 3, all the way up until n minus 1. And then we can cancel out common factors. And we're left with n times n minus n plus 1 in the numerator, which is just n squared plus n. Okay, and then that's the simplified form. Okay, so you may have seen this on the ACT. If you hadn't gotten to this yet, this is what it means. Okay, so questions about this example? Okay, your homework is W1 and W2, all the way up until 100. This covers everything that we did in kind of the first part of this class, so sequences, It does not cover factorials. Okay. There's no real good homework that I can give you right this second um, for factorials. I will give you one in the future. Uh, but right now, let's just focus on the sequences and series because that's probably the most important thing that we went over today. All right. So I'm going to leave this open for the next like minute or so. If you have any questions over anything we did, now is a great time to ask. Otherwise, you can start working on your homework. I will start a meeting in Teams. So if you have like specific questions, I can help you. But otherwise, that's it for the class. Okay. So again, I'll close this in the next minute or so. After that, I'll start a meeting on Teams, and I'll be able to answer specific questions. When will the matrix test be in? As soon as I grade it, I'm planning on doing that tomorrow or over the course of Easter. Okay, I've got your class, your senior classes, and then the junior class to grade. Um, so it should be really, really soon. Okay. Um, if you want to retake that trig test, that will happen over this Easter break. Okay, and I'll give you more directions on that tomorrow or today, and I'll send out an email. But if you are interested in retaking that trig test, you need to at least email me. That way I know like kind of who to reach out to, um, and I'll give you more directions on that a little bit later. Okay. So any general questions I can answer here. Otherwise, I'll close this and go to Teams. Okay, but I'll leave this open for the next like minute or so. All right, so I'm going to close this. I'll be in Teams. I'll start a meeting. If you have specific questions, I can answer them there. So I will see you there.